Welcome, welcome everyone to Reboot the World. We are so excited to have Dan Garrison and Carl Ducatz with us for Quantum Computing One-on-One. How are y'all, gentlemen?
Hey, doing
Good.
good.
Doing well.
Good. So y'all are up next. Take it away.
All right, perfect. Hi, everyone. This is Dan Garrison. I'm with a company called Accenture, which is a global consulting company. I play a couple of different roles in the company, but one of the primary ones is I'm executive sponsor for our global quantum computing program. Carl Ducatz is going to go ahead and help present today as well. He is the global lead for our quantum computing program, and he is a director with Accenture as well. So let's dive right in. A little bit of disclosure. 5 minutes ago, we got hit by a lightning storm. I lost power. I seem to be okay right now, but if I disappear, Carl is going to graciously jump in and take over. If you see a little disruption, that would be why. So let's talk about quantum computer. So first of all, we want to level set a little bit. When we're talking about quantum computer, this is an entirely new type of hardware. Okay, the general ideas behind the technology have been around for a long, long time, for decades, 100 years. But the way they work is they tap into these crazy behaviors of nature. We're going to talk about those a little bit more later on in the presentation. Quantum computers are in their early stages, but you can buy one today. They're expensive. I'm not sure many of us on the webcast would be able to afford one, but you can get them if you're a big company. And probably most importantly is we think that they have the potential to disrupt every industry there is, and we're going to help you understand why. Before we start talking about the technology, we want to talk about the business implications. And this is a conversation we have with our clients as we're helping them understand why they should be paying attention to it and what they should make of it all. So I'm going to start with math problems, actually. Don't worry, we're not going to geek out and go hardcore on any algorithms like that on the presentation today. But let's start with math problems being everywhere, right? I think everyone appreciates that they're embedded in everything we do, whether it's business, academics, everything. Math's everywhere. But let's put them into two very simple categories. The first, problems we solve every day. Maybe we can do them on a bar napkin. Maybe we can solve them on a calculator. It's on our iPhone or mobile device. Maybe we need a supercomputer, but we can still solve these problems every day in a reasonable amount of time. So that's the first category of math problems we want to think about. And then there's another category of math problems, and they are so hard, we never even really bother talking about them. They're just mind-blowingly difficult, but they're out there. Let's give some examples of the really hard stuff. So we'll start with encryption. I'm not going to make this a deep dive into cryptography, and I'm sure plenty of you out there know this topic well, but super simple version of how encryption works is I take two prime numbers, I multiply them together, and I get a really large number on the other side. But going backwards, taking that large number and finding the two primes, that's hard. That's very hard, actually. And it's the basis, more or less, for modern cryptography. All these things depend on encryption, whether it's your banking, whether it's cryptocurrency, Bitcoin, or it's email. Let's talk about Bitcoin or cryptocurrency in general for just a second to illustrate how hard it is to break encryption. The math behind cryptocurrency is so difficult, it requires such immense computing power, it consumes 1% of the world's electricity right now. The entire planet, 1%. That's 77 terawatts of energy a year. It's more than the entire country of Switzerland, Greece, or Israel. So it helps you appreciate that the math that our today's computers have to run in order to support cryptocurrency around the world is really, really hard. So how hard is it to break? Well, let's just take a hypothetical example. Let's say I had access to every computer on the planet, and my one job was to use every computer to break the encryption key that protects your banking. And I'm not talking about social engineering or zero-day exploits or any of that stuff. I'm talking about just brute force breaking that encryption key. If you had to guess how long it takes, it's probably quite surprising. It's about 14 billion years, again, to brute force just the encryption key that is protecting your banking. Another example of a hard problem is something called the traveling salesman. So this is a hypothetical problem. It's one of the most intensively studied optimization problems there is. It first was formulated in the 1930s, and the general idea is you got this traveling salesperson, and they're trying to make it around a series of cities in Europe. And what is the optimal route for them to travel? Well, 10 cities results in 300,000 different round trip options. So let's just bump that up by 5 more cities. It shoots up to 87 billion different round trip options. So this is an optimization problem that doesn't seem like it's hard, but it is very, very difficult with today's computers and today's math. How about caffeine? I'm allowed 1 caffeine a drink a day because I'm very, very high energy as it is. But we don't really know what this caffeine does to us or why it does what it does to our bodies. In order for us to truly understand what that caffeine molecule is doing, we would have to model every electron around every atom in that caffeine molecule. Now, that doesn't sound hard, but we can't do that. We would need a computer with today's technology that had as many bits as there are atoms on our entire planet in order to truly model that single molecule. And that's a fairly simple molecule, much less these long chain molecules that are at the heart of a lot of our problems in society today with pollution and whatnot. Now, building off from there, here's another example of a hard problem. Pharmaceutical drugs. So on average, drug discovery, to bring a drug to market these days in the US, it costs $2.4 billion, and it takes 10 years. The reason for that, there's a lot of things that go into drug discovery, but we don't have the ability to model accurately what all these drugs do. So instead, we have to do trials, clinical trials. Will it kill me? Will it grow Carl a 3rd arm? We don't have, with all the amazing technology, we have the ability to short circuit this right now. We have to do it in a time frame of 10 years at a cost of $2.4 billion. How about growing stuff? So if you think about how things grow in the dirt, well, I could take some manure, I could take a dead fish, I put it in the ground, and I mix that up, and I put a seed in there, and hopefully, eventually, I have something growing. And nature, it's doing its thing. That bacteria is breaking down in the soil, and it's creating the necessary fertilizer for that seed to be able to grow. It's called nitrogen fixation. So on the left-hand side of what you're looking at right now, this is the nature's way, the biological approach to nitrogen fixation. But in 1908, a process was created called Haber-Bosch that allowed us to synthesize an industrial approach to nitrogen fixation, which is spectacular. However, the problem is it uses 5% of the natural gas we produce globally, or 2% of the entire world's energy. We know we can do better. We know the math that has to be run in order to do better. But with our current computing technology on our planet, it would take about 35,000 years to run that math. So another example of super hard problems that we're just not talking about all the time. A couple of more examples of hard stuff. How about weather prediction? So right now, our best weather people, they got about a 90% accuracy 5 days out. 7 days out, they're about 80%. 30 days, I couldn't even find good numbers for it. You're making it up at that point. And major weather events in the US alone cost $807 billion in the last 10 years. Now, I'm not suggesting that predicting the weather would allow us to avoid all those costs, but they would allow us to take some preventative actions versus being surprised like we are often. But this is a hard problem. Again, we know how to write the math down to do these predictions, but they become so complicated so quickly, our current computers simply can't do it. Financial services is another industry that is just buried with all these different super hard problems. Portfolio optimization, optimal arbitrage, feature selection for credit scoring. If you're in this industry at all, you know what I'm talking about, and you understand that we only have the ability to run a certain level of complexity of calculations for these sorts of problems. Bug-free software. So software bugs cost us about $1.7 trillion a year. And some of the effects of putting bug software into a production environment are pretty well known. We've lost planes, right? We've had space probes disappear, massive financial services losses due to mistakes, electrical power grids going down. And the simple reason is that for all our advances in software development, which is what I do for a living, right? We don't have the ability to run every single permutation of data through every branch of code of a piece of software we might create. We know how to do it, but again, it's just not reasonable that we can do that in any practical amount of time. So what do these things all have in common? I just talked you through a handful of examples there. There's 1,000 more out there across every industry. But what do they all have in common? These are all problems that are theoretically possible to solve, but they would take such a ridiculous amount of time with today's technology. Instead, we settle for the best we can do. We aggregate things, we make assumptions, we consolidate data sets. We do the best we can because we simply don't have compute power to truly attack those complex problems. And they have a name. One name is they're intractable, and that means problems for which there exists no efficient algorithms to solve them. In computational mathematics, there's a fancier name. It's called NP-hard, non-deterministic polynomial time hardness. Here is the key thing that ties all of those examples back to quantum computing. Quantum computing allows us to attack these intractable or NP-hard problems. It's as simple as that. This new branch, new type of computing hardware allows us to attack mathematical problems that we don't even bother touching today. So it comes down to time and effort for select problems. And I want to be clear, quantum computing is not going to replace all of today's computers, okay? Quantum computing will focus on specific types of problems that, again, we can't even touch today. But quantum computing will not be replacing all of the classical or Newtonian computing technology we have on the planet right now. Those previous examples, and let me kind of frame it up, some of them I said took thousands of years to billions of years. Mature quantum computer is anticipated to be able to solve those same problems in minutes, if not seconds. It's not an exaggeration. So think about that for a moment. We're talking about being able to solve something that would take otherwise billions of years with today's technology in minutes, if not seconds, with the promise of quantum computing. So now you can start to understand and get an appreciation for the buzz and excitement around this and why it's predicted to potentially be the most disruptive technology humankind has ever created. So how does the magic happen? So I'm going to touch upon a little bit. So the whole quantum thing, okay, this is about nature at its smallest scale. And we're talking about atoms and subatomic particles here, because the world we live in, we know and recognize at a macroscopic level. And what I mean by that is, you know, this drink coaster on my desk in front of me, the weight of it in my hands, the effect of gravity on it, the texture on it. I'm not feeling and looking at individual atoms. My frame of reference is the trillions of atoms and the macroscopic experience I have of touching that object. But if you drill way down deep, if you go way down deep and you look closely, you find what are called quantum effects. So these quantum effects are what unlock the mathematical approaches that allow us to attack NP-hard problems. So let me say that again more slowly. These crazy quantum effects that happen at a super, super small scale offer an opportunity for us to run new types of math. That new type of math allows us to attack mathematical problems called NP-hard problems that we don't even bother talking about today. In my mind, this whole journey started around 1959. So if you don't know who this cat is, this is Richard P. Feynman. He is my favorite physicist ever. And he gave an awesome speech back in 1959 where he started to suppose that we might be able to tap into these quantum phenomena and create information systems out of it. And so some time went on. 1959 was a long time ago. And the primary reason is we didn't have math. You know, no one had created the math that could work against these quantum effects until this guy entered the picture. So this guy's Peter Shor. And in 1994, he was working at Bell Labs, and he created Shor's algorithm. And there it is. In 1994 is when I first became involved in quantum computing. I was pursuing a degree in chemical engineering, and we had a guest speaker, and he talked about Peter Shor and this algorithm he created, and I kind of got hooked on it, and I've been following it ever since then. So been a passion of the technology since Peter worked his magic back in '94. And then at that point, we began to ask ourselves this question, say, well, what if we could free computers from the limitation of sequential calculations? What would that do for us? Now, I know a lot of folks know a lot about computers on here, and you're probably thinking, oh, we got parallel processing and this and that, and I get it, we do, right? But at the end of the day, our classical computers are still processing things one at a time, which is fundamentally why there is a branch of mathematics that is super, super hard to run against those type of computers. Okay, so now you have a general understanding, right? We're talking about being able to solve really hard mathematical problems. These mathematical problems have the potential to impact every industry. It started back in the 50s, 60s, even though a lot of the concepts were around a long time before that. And the key point is that we've got these subatomic quantum phenomena that we now can tap into, leverage to run a new type of math, and from there, with that math, attack really hard problems. At this point, I'm going to turn it over to Carl. I think Carl's going to take us into a deeper dive and look at quantum computing versus traditional. Carl, you there?
Yeah. Hey, Dan. Thank you very much for the intro. So we'll dive right in. A couple of things that I want to cover first are some misnomers about quantum computing. Dan hit on a couple, but we'll just reiterate that quantum computers aren't planned to replace all classical computers completely, as far as we know today. At this stage in the game, they don't run on your phone, and they won't at least anytime soon. They're not breaking cryptography tomorrow, although the algorithms that Dan was mentioning, especially Shor's algorithm, is slated to do that at some point in time. Information does not travel faster than light, despite some of the things you may read about quantum effects. There's still travel time involved in quantum communications. They don't allow you to go backwards in time, very sci-fi-esque. That's not happening here. Dan mentioned owning a quantum computer could cost you a lot of money if you wanted a physical quantum computer in your data center, but you can access them through the cloud for relatively low amounts, or even there are some free services out there. You won't likely own one in your data center, but you could if you had a very strong rationale for getting one, put one in there. And they're not quite ready for production use yet, and probably won't be in the next month. But the timeline and the capabilities of quantum computers are rapidly growing. And so this is why we're very interested in looking at them and keeping tabs with how they're advancing. So just to also reiterate a little bit what Dan was saying about quantum computing versus classical computing and how they're different, I put together this little animation. And what it's meant to show is a classical processor has to, if it's doing a search or doing certain types of things, run one of those algorithms at a time and then get an answer and then compare all of the results. And when we're talking about a quantum system, we're actually talking about a device that can run multiple threads at the same time or simultaneously, or search multiple things at the same time or simultaneously. And so this is extremely interesting at a very fundamental level of compute. And as you scale that up, it allows you to do different things and tackle some of these problems that are intractable. So how does it do this, or why is it different? Well, at the lowest level, we're dealing with something called a qubit, which is essentially a subatomic bit that has different characteristics than what we would have as a classical bit. So whereas a classical bit can be on or off, it can be 1 or 0, this qubit is more like a sphere, and any spot on the surface of that sphere can be a value. So it's not just 1 or 0, but it can be any of this infinite set of values. And when you take multiple of these qubits and you combine them together, then you end up with a much more powerful computational system for certain types of activities. And it allows for some of this search space speed up or computational advantage. So the next thing that builds on top of this qubit in and of itself, and I love this example because it still catches me. This must be real, but it doesn't seem like it can be real. And check out the New York Times article there. But are these quantum behaviors? And so the first one is superposition. And this is the idea that when the qubit is polarized in a certain way, it's in an unknown state. And it can either be a 1 or a 0 when it's between when it's between 1 or 0, when it's in a spin state between those values. And this is one of the core effects that we use in order to do quantum computation. Another effect is tunneling, and this is the ability for the subatomic particle to transfer through things that would otherwise be impossible to transit through, or it allows essentially the skipping of certain aspects of computation. And this is really important. And then finally, the third effect is entanglement. And what this is that if two qubits are synchronized in a certain way, then if you change one, the other will change as well, or the other one will be affected. And this leads to some interesting nonlinear forms of computation. And with these effects combined, which are very well studied, well known, proven effects that we can repeat using physics over and over again, with these combined into one system, you now have a quantum computer. And we have multiple ways of creating these effects. There's superconducting loops, there's ion traps, there's many different ways of building a quantum processor using different types of physical components. And the jury is still out on which one is going to be the absolute best for building our quantum computers. But you'll see popularly superconducting loops and ion traps as the ones that you can access and leverage today for testing and experimentation. So what does a quantum computer look like? Well, one type, the superconducting type, you have this dilution refrigerator, and it's operating at a temperature lower than interstellar space. It's extremely cold inside. It gets progressively colder and colder as you go from the top to the bottom of the fridge. And you see these tiers. Inside is this chandelier-looking thing. And at the very bottom, it gets the coldest. And this is where your quantum processor sits. And there's a whole stack of electronics that allow you to send signals down to this processor and have quantum effects occur. Another type of quantum computer is, it looks like this. And there is an optical table where we're cleansing and purifying light, and then we're sending light into this vacuum chamber in order to shoot these ions with laser beams, and that allows us to spin the electrons within those ions and create computation. And so this is very, very different than what we think of as our traditional computational server or laptop or device. But amazingly, there are ways that people are already figuring out how to shrink these down and create them on a single chip, or having future architectures that make them more viable for operating at scale or outside of a laboratory or a specialized facility. But these are just a couple examples of ways that you can build quantum computers today, and validation that they do exist. There are two very predominant modes or types of systems that are available today in the quantum computing world. The first one is the quantum annealer. So this is a specialized quantum device that solves a narrow problem set, which is optimization problems. But even though the problem set that it solves is narrow, the applicability of optimization problems is very broad across many industries. And the idea here is that you can set a optimization problem up like an energy landscape, and you're trying to find the lowest point in that energy landscape, and then that's the most optimal thing that you can do in a given scenario. And what we say about this device is that if you have a problem that maybe, using the screw and nail example, if you have a problem that's a screw, you may want to convert it into a nail so that you can use your hammer, which is the quantum annealer, to solve a problem in this space and test it out and experiment with it. But it's good for specific things. The other type of quantum computers that are being built are gate model quantum computers or universal quantum computers. And these are are different in the fact that they are fully programmable, and this is how you program transformations of the quantum bits on those types of devices. And to give you an idea of what you're looking at, it looks kind of like a musical score. You read it from the left to the right, and each of the little notes on there is a transformation that you can do it to a qubit. And the important things are that these qubits on the actual device are high quality, that the qubits have high fidelity when you entangle them with another qubit, as I mentioned entanglement earlier, that you have more and more qubits available to you, and that you can create a very long score or a long set of circuits or transformations so that you can run a full-size program. And those are some of the attributes we're looking for as people create new quantum computers or quantum devices. So that's great. So Dan mentioned some of the stuff that they can do in the future, but what can they do today? Well, today, Google famously published that they have found an example where a quantum computer can solve a problem faster than the fastest classical computer on the planet. And this was a famous publication. I'll let you guys go read about it, but we've discovered this idea, or we've reached this idea of quantum supremacy, where there is a quantum device that is faster and more capable than a classical computer, but only in a very, very, very niche problem that doesn't apply very broadly. And so that's quantum supremacy, but we have yet to discover a quantum advantage. So this is where we can use quantum computation more generally to solve use cases that matter to people in business. So we're looking for those. We're looking for these use cases, and we're looking for a device that enables us to do them. So what do we do? So to I guess clarify that example a little bit more. If you look at quantum as a theoretical concept, the ability to have proof of concepts, the place where it starts being useful, and then the area where we actually have superiority, we're somewhere in here right now. We call this the NISQ era. So we've got proof of concepts. We've proven that the technology is faster and capable, but we don't have a place to apply it that it's useful or better than what we can do classically yet. And so this is what everyone in the industry is striving to improve upon, find, grow, and create. So another layout of what that looks like is where are we headed and what can we do today? Being educated on this, building software that leverages quantum systems, but not yet providing advantage, and setting yourself up for success in the space is really some of the key things that you can do. And then as advantage is found, we'll be able to leverage quantum and classical computers to deploy that advantage, and we'll start to see some of the first world applications come out where we use quantum to solve really, really hard problems efficiently. And so a lot of this we believe will start in chemistry and material science, then move into more of the optimization problems and supply chain, and finally we'll get into an era where we're superseding our existing machine learning technology and potentially breaking some of the security algorithms that are available. So how do we know this is going to continue? There are a lot of investments going in the space. There's governments around the globe investing in quantum computing. There's venture capital that is growing the quantum ecosystem with startups and making sure that they progress. And then there are also corporate entities that are building quantum devices and continue to release better and better quantum devices year after year and improve the algorithms that are available and the access to those devices. Additionally, we see more companies getting involved in their quantum strategy, and there are many different things that you can do to be a part of the quantum ecosystem today, whether it is working internally to identify use cases, or attending conferences and understanding the technology, doing research and discovering new algorithms. So the community is growing, and companies, businesses, students, and governments are all looking at these different types of activities and getting ways to get involved. So what does a project look like if I wanted to tackle quantum computing today? Well, you would usually start with one of these high-level categories where we know quantum applies. And the first one is machine learning, as I mentioned. If you're looking at more of a longer-term view, optimization type problems is a second area. And then simulation and sampling, this is effects in the real world that are quantum in nature that we can also simulate or run on a quantum computer. And then finally, cryptographic researchers or security researchers are also investigating and looking into the technology in this space. Usually, you will want to, when exploring this, you'll need a team of people that understand quantum computation specifically. So one of the members of your team will be an information scientist who understands the hardware and the parameters and the algorithms. You'll want an integrator, someone who knows the application toolkits and how to integrate those at higher levels of the stacks and how to code them around them. This is typically someone who understands back-end engineering. You'll want a system architect who can translate this back-end and low-level code up to a higher application layer, and then you'll build a presentation layer in order to allow people to access and explore the algorithms and system that you've built on Quantum. Some examples of this that we have done are a truck routing optimization solution that takes multiple trucks and multiple depots and finds the optimal path for those trucks to make their deliveries. And another example is robotic arm path planning. So this takes a parts or a welding schedule for a robotic arm, and it figures out what the most optimal path for it to do the welds are and increase the speed of a production line. Another example is in the pharmaceutical industry with small molecule comparison. So we can take two of these small molecules, represent them in a graph format, and do an optimization between the conflict of those two graphs and match what the similarities are between those two molecules. And this is helpful in the drug discovery process at the very beginning when trying to figure out which molecules to use in that 10-year process that costs $2.4 billion that Dan mentioned. We also have done some work in protein folding. So this is a little bit different, but this is taking a protein, testing the different folds in order to find the best ways to dock with that protein. And again, in the drug discovery space. And then another one that was really interesting was looking at something like a kidney exchange network. This is where a donor and a recipient pair who aren't necessarily a match for, say I was giving someone my kidney, I wasn't a match for them. I could enter this network and match with someone who could take my kidney, as well as the pair would have someone who could donate to the person I entered the network with. And the optimization here is how can you find the ways to get the most people, the most kidneys, and save as many lives as you can. So we were experimenting with using quantum computers to do this type of optimization. Portfolio optimization, this is kind of an obvious one, but picking the most stocks, the best stocks that will yield the best results for your portfolio, building the algorithms and solutions behind that, as well as risk analysis. So ensuring that the profitability of an investment that you make is within a risk tolerance or threshold, and there are many factors and optimizations that go into that. The last thing I wanted to touch on was what is the deal with security and what's the intersection between quantum computing and security. And Dan mentioned earlier Shor's algorithm, this factoring algorithm, and then there's also a famous search algorithm called Grover's algorithm. And Shor's algorithm is really bad for security, and Grover's algorithm is pretty bad for security, and we'll talk about both of those. But these are the new tools if you're, I guess, a black hat that are in your toolkit. And so, as mentioned previously, classical computers can easily combine large numbers, but it's really hard for them to reverse from those large prime numbers back into, or from the large number back into the primes, whereas this is easy for a quantum computer using Shor's algorithm. And so what does that mean? That means if someone's eavesdropping on your communications, they can steal the keys, the asymmetric keys that were used for your communication, and also capture the data that you're communicating along the way. And then using Shor's algorithm, crack those asymmetric keys and then get the symmetric key that allows them to decrypt the data that you sent, and essentially harvesting the information from your communication, or even in some cases, if the technology is fast enough, intercepting and changing the contents of the communication. There are algorithms that are being developed today called quantum safe cryptography algorithms that don't rely as heavily on that factorization. And although a hacker may still be able to eavesdrop and steal the data that you're transmitting, they wouldn't necessarily be able to access that data. And so these quantum safe algorithms is something that people are exploring and looking at how to implement in order to protect themselves, even today, from future quantum computers that could potentially, that people could potentially be harvesting their data today for those future quantum computers and be cracking it later on. Another thread in protecting yourself against these eavesdroppers who are stealing the content is an entirely different way of using quantum systems, and this is called quantum communications, where they can use the entanglement property that I talked about earlier in order to do this key exchange. And then they can identify when someone is eavesdropping on their line and not do the communication, or choose a different outlet for the communication such that it is not compromised. So this is another way that quantum effects are available to potentially secure us in the future. On the opposite side of this, so if we're not talking about live communications with asymmetric keys, but we're just talking about data that you're storing somewhere in your database, hackers could steal that data and then use this Grover search algorithm to find a key to that data, or find a way to decrypt that data. And this is another type of this harvest now, decrypt later attack, when a quantum computer has sufficient size in order to be able to do the search for that key. And in general, the general device today is to double your key length in order to make it much more difficult for a Grover search algorithm to find these keys. Shor's algorithm has, for the asymmetric keys, is much more powerful in cracking that type of cryptography. Grover's is still very powerful, but the general advice today is to double your key length. Now, I urge you to conduct your own risk assessment and don't just take this advice as it stands, but please do look into this in more detail and discover it if this is something that you are looking to explore. But that's generally the information you need to know at a high level behind what quantum is doing to security today. And also, to kind of sum this up, as far as what's available today, the projections of when quantum computers will be able to break classical cryptography, or the cryptography we use today, the advice varies, or the timeline varies depending on who you talk to. There's a really good publication that walks through the size of quantum computers that we would need to use, and here are some kind of high-level hand-wavy estimates on when those devices could potentially be available. The challenge is that if your data is being taken today and it needs to be protected even 10 years from now, then you could potentially be at risk. And so what you should consider, or what you should start to think about and work with your vendors and partners on, is to discover what type of data you have, and if it needs to remain confidential indefinitely, and what actions you need to take. Or if your risk tolerance is different, you may take a different approach to dealing with this new potential threat. That's I guess the info on quantum security. And I think with that, we're gonna pause and take questions and answer anything that the audience wants to know about.
So we're going to give the Campus Arrows a couple of seconds. Campus Arrows, if y'all want to go ahead and type in any questions you have for these two gentlemen into the chat.
And that'll be in the live comments, right, Jen?
I'll be reading them out to you
got it.
with any questions. But if maybe someone sees this video not live as a pre-recorded, are they able to reach out to y'all with any questions directly, or do you have any resources for them that they could go to look up on their own?
Yeah, so a couple of thoughts. People can absolutely reach us out to us. Carl and I talk to everyone from students to CIOs and CTOs, government. So we love talking about this topic. We love answering questions. We've got a great network of partners in the industry. So we talk to the big players in here, and happy to provide any redirects for things people might have interest in if we can't answer ourselves directly. As far as resources, there are a ton of resources that are available out on this topic. It was mind-blowing, even, gosh, Carl, like probably 8 years ago, how many software solutions were already popping up. And this is before all the advanced stuff from IBM and Microsoft and everybody else that's coming online or has been online. So there's no shortage of resources that, as an individual, if you want to get into this and become smarter on it and play hands-on, we can offer you a redirect there as well. We have a couple of thoughts on kind of the usual questions we get. So if you don't have any coming in yet, Jen, we'll pause just for a moment or two, and then we'll throw out some of the, well, what about this questions we've gotten when we presented this in the past.
Let's go ahead and do that. I don't see anything coming through at the moment, but that doesn't mean that someone's thinking. So why don't you go ahead, move forward?
No problem. So kind of related to the security timeline topic, what's interesting is that, as Carl said, there's a variety of perspectives on how long it will be before quantum hardware advances to the point where it can truly threaten cryptography. And the good news is that there are quantum proof algorithms that are being created. They're not standardized yet, but we will have them. But here's one of the concerning things. When we go and we talk to the academics in this space, we often hear this kind of theme of 10 and 10. And what that means is that the analysis has been done, and the typical Fortune 500 company, on back end, these organizations, they've got just massive number of computer systems, right? Whether it's in the cloud or in a data center they own. And across these computer systems, they're just dripping with encryption, right, of a variety of forms. And so it's been estimated that it'll take about 10 years for the average Fortune 500 company to retrofit every single computer system such that it has a quantum-proof algorithm. That's a long time. It seems kind of mind-blowing, but if you think about it, you just can't go into a production environment and make this code tweak, right? These things have to be implemented, tested, deployed, outages, all that sort of stuff. And it's quite disruptive and it's quite costly. So 10 years. Now the other 10, so I said it was 10 and 10. The other 10 is that the average estimate for how long experts feel it will be before we have quantum hardware advance to the point where we can actually attack today's encryption, it's within 10 years. So what that effectively means is that if organizations are not starting to look at this and retrofit systems right now, we may very well have a Y2Q event, right? So in the year 2000, there was this big event called Y2K, and there was predicted that because computer systems had not historically been created to be able to support the year 2000, the turnover of that date, that the whole world was going to come to an end and power grids were going to go down and ATMs would spit out money and all these other, kind of sensational concerns. Well, Y2K kind of came and went, and it was, you made a little blip here and there, but it was mostly quiet. But here's why. It was because there was a ton of retrofitting. There's a ton of remediation that happened in the years running up to Y2K. Now we've got Y2Q, except we don't know exactly when it's going to be. So if there's an advancement and a major breakthrough from any number of the hardware players in this space that shapes and brings that 10-year window down much smaller, we are going to find that organizations around the world are going to have to make it a focus and a priority to go ahead and respond to now the threat that quantum computing brings to encryption as it stands today. So that's one example. Jen, do we have any questions coming? I've got a couple other I can share, and I'm sure Carl does as well.
So we do have one question. Juan asked, does conventional computers, are they able to run quantum safe algorithms?
Carl, I know you were anxious to answer this one, so go ahead and talk about hybrid and synthesization.
Yeah, and so yes, absolutely. The idea that these quantum safe algorithms can be implemented on classical computers is absolutely right. That is what the NIST competition is all about, and they are approaching finding some of the finalists that they will standardize for these algorithms that can run on classical devices. There are modifications or updates that will have to be made. Some of the algorithms are a little bit more memory intensive, and so people who are creating IoT devices may have to consider these new algorithms in their hardware strategies in order to be able to implement them effectively. And just the same, if you're implementing them in a large server environment, you have to consider different performance accelerators in order to make them work. A lot of the chip architecture today is designed around doing cryptography efficiently, and there's co-processors in there to make sure that it all runs at speed and at scale, and all of those low-level systems need to be updated, and it is concerning for a lot of the IoT devices that don't get firmware updates and can't be updated on how they will be remediated when the standard is created. But it is meant to run on classical systems.
Great. So it looks like that's all the questions that are coming through for right now. So again, they can definitely reach out to y'all if they have any additional questions. So thank you so much for your presentation. It was very insightful, very educational. I definitely learned a couple of things myself. So thanks again, guys.
Okay, thank you for having us. Have a good day, everyone. Take
Bye.
care.
And so now we'll do a couple of shout outs to our sponsors.
The challenging times faced by business these days have shown the difficulty in managing HR issues and maintaining profitability. Keeping focus on the core business and finding the right partners to help with ancillary functions like HR administration is why more than 500 companies across the country turn to Trion Solutions. Trion relieves the stress and burden of HR administration so companies, small to large, can stay focused on why they went into business in the first place. Small companies turn to Trion to manage their payroll and taxes, benefits administration, workers' compensation, and regulatory compliance, so they don't need to build a big HR department. Larger companies add Trion as an extension of their existing HR staffs, achieving efficiencies and enhancing the bottom line. Check out Trion at RelyOnTrion.com and receive a free consultation from one of its business advisors. It'll be the best business decision you'll ever make.